Hello and welcome to this lecture. This lecture we are going to start looking at sinusoidal functions. So now sin x and cos x are very basic functions. Many of us learn it in school with the triangle, right angle triangle, opposite side by hypotenuse is sine, adjacent side by hypotenuse is cos and all that. We are going to quickly do it. I am doing it just for completeness for people who may have forgotten some of these things. We will do it real quickly and do a quick summary of this, but we will do it in a slightly maybe different way from strongly calculus sort of point of view. Okay, so let's get started. So here is the unit circle, our familiar unit circle here, and then there is this angle theta that we have, and of course this is length of arc which is theta and radians, right? I'm just pointed that to you. Now if you want to compute this length of arc as an integral, right? We know an integral formula for the length of the arc, right? We have to start here, no? At this point, right? That this x integral from this x to 1 of 1 by root of 1 minus x squared or something, right? So that's going to be my length of this arc. We saw that in a couple of examples earlier also. So once I give you the angle theta, you really need to know what the length of this line is, isn't it? And maybe also length of this line. Anyway, length of this line and this line are connected because this is a right angle triangle. So it's very natural to define the length of this line and the length of this line for an angle theta, because that clearly, I mean, that's the length of the arc, theta is the length of the arc, and the length of the arc is also connected to where this point is and what is the length of the lines, etc. Okay, so we make this very natural definition for a particular angle theta. This point may be x of theta comma y of theta, right? So that x of theta is the length of this line and y of theta is the length of this line, right? So that's very clear and obvious. So these, why do I say x of theta, y of theta? Because as I vary theta, this point also changes, okay? So clearly these are functions of theta. There's no doubt about it, and they don't depend on anything else. It's a unit circle. So this x of theta, y of theta clearly depends only on theta. There's lots of things you can say about this function. So these two x of theta and y of theta are what are defined as cos theta and sin theta. Okay, so this is the same as the triangle adjacent side by hypotenuse. Remember, the hypotenuse is 1, this length. The hypotenuse in this right angle triangle is 1 because it's a unit circle. That's the radius. So it's 1. So cos theta is simply x of theta and sin theta is y of theta. So visualizing sine and cos on the unit circle is a very important thing. So in all, particularly in electrical engineering applications and circuits and sine waves and cos waves and all that, it's important to always think of the sine and cos as these these lines on the x and y axis at an angle theta when you have an angle theta. Okay, so this is an important definition. Now it's very clear that sine square theta plus cos square theta is 1, right? This is a right angle triangle, hypotenuse is 1, Pythagoras theorem directly gives you that result. And here comes the next result, which we know from the calculus, that the arc length, which is theta, is actually integral from cos theta, right? So cos theta is the length of this line. So I start at cos theta and go up to 1 and find the length of this arc. This arc is root of 1 minus x squared and root of 1 plus f prime of x squared. You remember that formula for the arc length. It's integral cos theta to 1 by root of 1 minus u squared du. and theta from 0 to pi, this formula sort of directly clearly works, right? So also remember, if theta is up to pi by 2, cos theta is going to be positive, right? So x of theta is positive. When it crosses pi by 2, cos theta is going to be negative and all that, but that's okay. That definition is okay here. Integral from cos theta to 1 by root of 1 minus u square du. So these two formulae are important. Sin square theta plus cos square theta equals 1. Many people know this is reinforced from school a lot. This maybe is a little bit more non-standard for the arc length. It's a direct formula, but then this formula is useful since we know integration. We have studied integration and all that. This can also be a very nice way to define cos theta and relate the angle to the cosine of that angle. Okay, cos is, by the way, cosine. Sine is sine, and these are names that have a lot of history to them. You can look it up. Okay, so let's see a few examples, right? So it's easy to see a few examples. First thing is, if theta is 0, right, I have this horizontal line. So sin theta is 0, so sin 0 is 0 and cos 0 is 1. Okay, so you can see that when that point is all the way here and this is a horizontal line, there is no vertical component to it. So sin 0 is 0 and cos 0 is 1. So when you go all the way to pi by 2, something interesting happens. When you go to pi by 2, you see sin pi by 2 is 1 and cos pi by 2 is 0. Okay. So all these I am sure you've seen numerous times before. I am just showing you on the circle that you can always see very quickly that sin pi by 2 will be 1, cos pi by 2 will be 0. Supposing you go all the way to pi, okay, if you go to pi, you see that sin pi is 0, there is no vertical component here, but cos pi has gone minus 1. Okay. On this side, cos will be negative, right. So it's going to, if the angle is all the way here, then this will be sine, that will still be positive, but cos has gone negative. It's on the negative x-axis. Okay. So if you go to 3 pi by 2, which is this line here, sine 3 pi by 2 now is negative. So once you come beyond pi, sine will go negative and cos will be negative as well up to 3 pi by 2. So you have minus 1 for sine 3 pi by 2 and cos 3 pi by 2 is 0. There is no horizontal component here. Okay. As you go into the fourth quadrant, theta goes into the fourth quadrant, you see more interesting things end up happening, but that's okay. We'll come back and see that later. The other interesting thing you can quickly derive is sin pi by 4 and cos pi by 4. So what is sin pi by 4, cos pi by 4? Let me just quickly write this down. It's very easy to see. So if you do pi by 4, that's the y equal to x line, right? That's pi by 4. This is the unit circle, and this is x, and this is also x, right? So and this is 1, isn't it? So x squared plus x squared equals 1, which means x equals 1 by root 2. So this is 1 by root 2, 1 by root 2. So cos pi by 4 is 1 by root 2, and that's the same as sin pi by 4. Okay. So you can quickly see that this is true, and that's the result that we have here. So cos pi by 4, sin pi by 4 is 1 by root 2. Then once you have cos pi by 4, the same, if I go to 3 pi by 4, it's on this side, you see it will be minus 1 by root 2 for cos and plus 1 by root 2 for sin. And if I go to 5 pi by 4, both sin and cos are minus 1 by root 2. Okay. And then if I go to 7 pi by 4, I see cos is 1 by root 2 positive and sin is 1 by root 2 negative, minus 1 by root 2. Okay. So you see that how the values of these sines and cos can be derived in some cases, at least 0, pi by 4, pi by 2, pi 3 pi by 4, all these things are sine and cos are very, very easy to find. Once again, very standard. If you want, you can convert it to degrees and quickly see how. And I hope you see how these signs work out. If you remember the circle, the signs will be very obvious. You just have to see which quadrant it is in, and then you will know the sign of cos and the sign of sine. Okay, whether it's positive or not. Okay, I keep saying sign of sine. I hope you understand. SIGN is also sine, SINE is also sine. So the positivity, negativity is what I mean by saying the quadrant determines what is positive, what's negative. We will see that also more formally. Okay. Quick properties. I don't think the plot is going to come now. Plot will come a little bit later. Quick properties on the sine and cos. First thing is bounds. Whatever you do, sine theta is going to be between minus 1 and 1, and cos theta is going to be between minus 1 and 1. You can't exceed that. It's very obvious on the circle. The length is not going to be above that. Next, very interesting property is periodicity. Okay. Sine of theta plus 2 pi. Okay, if you add 2 pi to the angle theta, right, you rotate it and you come back to the same point. So sine will be the same, cos will be the same. Even if you subtract 2 pi, right, you're going anti-clockwise rotation or clockwise rotation, but you come back to the same point. Okay. So whether you subtract or add 2 pi, you get the same function. So that is called periodicity. So at theta you have a value. Theta plus 2 pi you have the same value, theta plus 4 pi you have the same value. With a periodicity of period of 2 pi, the same value is repeating. Okay. So that is periodicity, and it's a very, very powerful property of the sine and cos function, and that comes from the way in which we define it on the circle, isn't it? Okay. So here is the generalization. Theta plus 2n pi is sine theta and cos theta plus 2n pi is cos theta. Okay. So again, I mean, n can be any number, 0 or integer, 0 plus or minus 1 plus or minus 2, and this is always true. Okay, that's periodicity. It's nice to see. Now comes sine and quadrant. I was talking about it in the previous slide also. So you see here, if theta is between 0 and pi by 2, you are in the first quadrant. Both sine and cos are positive. Okay, so you are in the positive y-axis, positive x-axis. Everything is positive. So here, if you go to the second quadrant, pi by 2 to pi, right? Sine will still be positive, it's on the positive y-axis, but cos goes negative, it's on the negative x-axis. Okay. If you go to the third quadrant, sine and cos are negative, because the the angle is here, you are on the negative x-axis, negative y-axis. Okay. If you go to the fourth quadrant, 3 pi by 2 to 2 pi, you see that cos is positive, but then sine is negative. Okay. So another way to remember this is, above the x-axis sine is positive, below the x-axis sine is negative in some sense, and to the right of the y-axis cos is positive, to the left of the y-axis cos is negative. So these are things to quickly see. So if I give you a point x comma y, and if I draw a line from the origin to the point x comma y, you can easily say what will be positive, what will be negative. Okay, that just depends on the sign of x and y. If x is positive, cos is positive. If y is positive, sine is positive. That's all. Okay, so as simple as that. So this also gives you a symmetry. If you are at theta, if you do minus theta, okay, you go to the other side, you see that sine will go negative because you're on the y is positive. If you do minus, y goes negative with the same theta. So sine goes, the absolute value of sine will not change, but the sine will go negative. Okay, the positive value will go negative value. I hope you can see that this just comes from this this observation. And cos of minus theta will be cos theta. Okay, cos, if you go, the angle is here. If you do minus of that angle, you're not changing the, you're not flipping the x value, right? So you're flipping only the y value when you go to the negative y angle. So cos gives the same angle. Maybe I should draw a picture here just for you to see. So if I have a positive theta here, and if I look at the negative theta, right? So you have the same thing here, right? So this x remains the same, and this y becomes minus y, isn't it, for minus theta. So sine will go negative, cos remains the same. Okay, so it's a very easy, simple observation for why you have this symmetry. Okay, so these are interesting properties. The plot will come later. The title is wrong, but you can see all these properties are very, very crucial, and I'm sure many of you know these properties very, very well. Okay, so let's see the plot. So sine and cos have this very famous wavy plots, and I want to show how, just illustrate how it comes from the circle in this nice way. Okay, so let's stop it. Let me go back and do it, play it for you. Okay, sorry. Okay, so here is 0. Right now I'm at 0 degrees. I'm going to plot the sine and cos starting at this point and keep the circle here and show you how, as the line moves, these points vary. Okay, so this is the 0 degree angle. So sine is at 0, sine is blue, and cos is green. Green is at 1. Okay, so this is the length which is plotted here, that is 1. Now if I go, okay, wait. If I go one little bit above, okay, so you notice here, sine is just this height, right, small height here. Cos is this length. Okay, I'm plotting this length from here, okay, from this point. So it is that length. Okay, so it's got a little bit below the previous one. Sine is a little bit above. Okay, so you can see that. Okay, so let's go a little bit one step forward. If you go one step forward, you see that the angle has increased a little bit more, and sine has increased a little bit more. Cos has decreased, right? So that's what's showing here, right? So this length is cos, it has gone down, and this length is sine, and it's gone up. Sine is probably easy to see. You can associate with this length directly. Cos is a little bit more. You have to rotate it and see, so it's a little bit more difficult, but you can see that. Let's go to the next point. So you see more increasingly sine is increasing, cos is decreasing. It keeps on going like this. So at this point maybe you can see it very clearly. So you see the blue length here is the length of the sine, and the green length here is the length of the cos. Okay, so slowly as they increase, at some, that's where it's close to 45. So that point is like almost 45 degrees. So there sine and cos are equal. Okay, so you saw how that was decreasing from 1, this was increasing from 1, and they meet here. And then if you keep going further, they cross, and sine becomes greater than cos, above 45. And then it keeps going, up to 90 degrees. At that point, this green has come to 0, right? There is no green length anymore, and the blue has gone maximum. So sine is maximum, and cos is 0. Okay, so that's the point of sine and cos. And then you can keep going further. Now if you go further, you notice that cos has gone negative. Okay, the green has gone negative. Sine still remains positive, but it's decreasing. Okay, it keeps decreasing like that. So you can see that cos is going more and more negative, sine is going, sine is decreasing, right? The blue is decreasing, the cos is going negative, right? It's gone on the negative side, and then you keep on going like this. And the next interesting point, maybe there is a point here, like maybe at this point, these two are same magnitude. 1 by root 2 is like 135 degrees, like 3 pi by 4. Okay, so you have 1 by root 2 here, minus 1 by root 2 here for cos. Okay, but these two are same in magnitude, and then you keep crossing that. And the next interesting point is pi. Okay, this is pi. I don't know if I can get rid of this. These things, can I hide them? Okay, no, I think I can't hide them. So you can see this has gone to minus 1. Maybe I should have made this a little longer. Anyway, this has gone all the way to minus 1. Cos has gone to minus 1, sine is at 0. So that's at pi. Then beyond pi, oops, what did I do? Beyond pi, you see again sine has gone negative, cos is still negative, but its cos is like becoming lesser in negative direction. And likewise, if you keep going, there is a 5 pi by 4 point where they meet, right? 5 pi by 4 where they meet. Both of them are the same, both are negative, and then it increases again. I mean, cos keeps increasing, sine keeps decreasing. So you go at 3 pi by 2, cos is 0, sine is negative. Okay, and then you further keep increasing. You go all the way up to 2 pi. At 2 pi, you see sine has become 0 again, and cos has become 1 again. So this is considered one full cycle of the sine wave and one full cycle of the cos wave. Okay, this is how we describe it. So that you can see, why do we say cycle again? See, that's clearly cycling of this radial line once around the circle, right? You do this cycle, it's like pushing this pedal anti-clockwise once, and the sine goes like that, cos goes like that. Okay, and in fact both these are actually the same shape. We'll see later that these are the same shape shifted with respect to the other. So really they are not different curves, but we traditionally see both sine and cos. So we like to define both of it and keep it going. But both of these are exactly the same. They are shifted by pi by 2 actually, if you think about it. Okay, so but these are just this very nice illustration, and you have this smooth wavy picture of sine and cos. It creates a lot of interesting things in us. Okay, so let's move on. So I showed you the plot. Now this is a complete plot. I showed you from 0 to 2 pi. You can also do 0 to minus pi, right? So a very standard way of drawing sine and cos is from minus pi to pi. So a lot of people like to write, at least in EE, we like to write from minus pi to pi, not 0 to 2 pi. It's all the same, right? Because there is a periodicity with 2 pi, it's enough if you pick any 2 pi interval and plot sine and cos. After that, it will just repeat. Okay, so if you see here, the sine is like this, right? What will happen after 2 pi? You say take the same shape and shift it there, and it continues like that. Okay, same thing with cos. Cos from minus pi to pi will have this shape. What will happen after that? You can take the same shape and shift it around this side and that side. So these are smooth curves. You can keep on. You'll see this are really smooth. They look smooth, and we'll also show later when we find the derivative that they are really smooth. You can keep on differentiating them. So very smooth functions, and they're bounded between minus 1 and 1. And you can see the shape, right? So this is this famous wavy shape of sine, minus pi by 2, pi by 2, pi. These are all interesting points where you can see what shape it takes. Okay, so this point where it meets is pi by 4, and you can make some conclusions from that. So this is a plot, and I would urge you to use, I've done all this in Desmos. I'll urge you to use Desmos and play around with these things, and you'll see and understand them much better. Okay, so a few problems. I'm not going to spend too much time solving them. I hope you have enough expertise with sine and cos. Just basic problems. This you have to use just the 2 pi property here. This is just sine square plus cos square equals 1, and this is just from the plot. When will sine theta be greater than or equal to cos theta? You can also do it from the circle. When will sine theta be greater than cos theta? You can do from the circle. Be mindful of signs. Positive, negative. Be careful, but you can see quite easily when sine theta will be greater. Till 0 to pi by 4, you see cos theta will be greater. From pi by 4 onwards, sine theta will overtake cos theta, and then you can see where it overtakes back again, and you can go along with that. Okay, so that's That's these nice problems to think about. Okay, thank you very much.